All right, the objective of this video is to apply the segment length properties. We've done angle-arc relationships. We're going to go ahead and look at the segment relationships inside of a circle. So the first theorem says if we have two chords that intersect inside of a circle, the product of their parts is equal to each other. And so looking at the first diagram, if you have chords AD and CB intersect each other, then we can say that segment AE times segment ED is equal to BE times CE. And if you take a look at the diagram below, we can use similar triangles actually to prove this property. And what we have here are some congruent angles to each other because they are vertical angles. And if you look here, we have two angles that are congruent because they are inscribed to the same arc, so they are both equal to each other in measure. And then you have that these triangles by angle are similar to each other, which then creates this proportional relationship of AE and EC to BE and ED, which again leads to that product of parts is equal to each other. And so you guys can take a look at the examples. I'd ask you to consider looking at example 1 on your own. And if you have that these chords intersect each other, then we have that the parts multiplied together are also equal to each other. So 3 times 2 equals 4 times x. Multiplying 3 times 2 is 6. Divide both sides by 4, we get 6 over 4, or 3 halves is equal to x. Don't forget those labels. Take a look at the parts B and C of this example. Think about what they would be. And once you have a good idea of what they are, go ahead and resume the video. Looking at example B, I don't know if it was clear to see, the radius of the circle is 7. This smaller part of the segment is 2. The remaining part then is going to be 5. So we have 5 and 9 are the two parts of the first chord. 6 and x are the two parts of the second chord. So 5 times 9 equals 6 times x. Divide both sides by 6, 45 over 6. Divide both the numerator and denominator by 3. We get 15 over 2 centimeters, or 7.5 centimeters for x. And the last example, here, pretty straightforward relationship. Congruent segments 6 and 6 will equal 5 times x. Divide both sides by 5, you get 36 over 5, or its decimal equivalent is equal to x. And just to reiterate, this relationship is stated at the top of your note sheet here. The two parts of the chords multiplied together are equal to the two parts of the other chord that they intersect. The second relationship that we have here stems from two secant segments, and ultimately it says if two secant segments share the same endpoint outside of the circle, and I'm going to go ahead and zoom in here on the diagram a little bit, the outside part times the whole on one of the secant segments is equal to the outside part times the whole of the other secant segment. Again, a nice proof here of similar triangles establishing the corresponding parts are proportional to arrive at this product. The final relationship stems from the secant segment and tangent segment sharing a common endpoint outside of the circle, and ultimately the relationship here, and again I'm going to zoom into the diagram, is that the tangent segment multiplied by itself is equal to the outside part of the secant segment, as with the previous theorem, times the whole part of the secant segment. Again, there's a really nice proof here. It's pretty straightforward in terms of how we can establish the two triangles are similar and the corresponding sides to create this product are equal to each other and proportional, but we're going to go ahead and focus on applying it. So you guys see examples at the bottom of this page here where it shows these relationships played out. I'd like to go ahead and just have us try the Now You Try Some section to finish up this concept. First example, we have a secant-secant relationship with a shared endpoint outside of the circle. So we know we can take the part times the whole of one secant segment and set it equal to the part times the whole of the second secant segment. So 2 times the whole segment is 2 plus x equals 3 times the whole segment, 3 plus 3.5 is going to be 6.5. Carrying out the math, we get 4 plus 2x equals 19.5. Subtract 4, 2x equals 15.5, and dividing by 2, we get 7.75 centimeters is the value of x. Taking a look at the second example on this page, we have another secant-secant relationship, and with one of the secants, we have 3 congruent parts where they'll all be labeled 4 centimeters. And so again, the outside part of the secant times the whole will equal the outside part of the secant segment times the whole. So 6 times 6 plus x will equal 4 times 4 plus 4 plus 4, or 12. Simplifying, we get 36 plus 6x equals 48. Subtracting 36, 6x equals 12. X is, a nice 2 centimeters. And last but not least, we take a look at 2C where we have a tangent-secant relationship. And so to recall, we take the tangent segment times itself, and we set it equal to the outside part of the secant times the whole secant segment. And so we'll have 12 squared equals 5 times 5 plus x. We get 144 equals 25 plus 5x. Subtract 25 from both sides. 119 equals 5x. And so we can divide by 5 and say 119 over 5, or 23.8 centimeters is the value of x. That concludes the 3 segment length properties inside or outside of a circle, and we'll go ahead and practice this concept.